Welcome back, everyone. Now that we understand clustering as a general idea of unsupervised learning, let's dive deeper into a specific clustering algorithm, that is k-means. In this lecture, we'll talk about the history, intuition, and theory behind k-means clustering. We're going to start off by briefly going through a tour of the timeline of the development of the history behind k-means clustering, and afterwards, we'll dive deeper into the main method and concepts by walking through an intuition of how k-means clustering actually works on unlabeled data. So this really all begins with Hugo Steinhaus, who was the mathematician who began laying out the groundwork for clustering methods. And during the 1940s, Hugo Steinhaus was a Polish mathematician and professor. And of course, living in Poland during the 1940s, that means that during World War II, he was actually in hiding from Nazi occupation. And even more impressive than that, he actually still taught clandestine mathematics classes from memory, since higher education for Polish people was forbidden during World War II by the Nazis. And he even established statistical methods for estimating German casualty rates based simply on relative frequencies of obituaries in local newspapers based off the last names that he saw were German in those obituaries. So after World War II, he helped establish the mathematics department at the University of Wrocław. And it was at the university where he began to develop the ideas that would become the foundation of k-means clustering. Now, this was just a brief little snippet of his life, but you should really check out his Wikipedia page for more interesting stories from his really incredible life. But afterwards, when he's done laying out the groundwork, in 1957, Stuart Lloyd of Bell Labs actually developed the standard algorithmic technique for clustering that is related to k-means. It should be noted, though, that Lloyd didn't actually publish his technique in a journal until 1982. And after Lloyd of Bell Labs discovered it in 1957, but before he published in 1982, in 1965, Edward 𝒂𝒏𝒔 published the clustering technique, and thus both Lloyd and 𝒂𝒏𝒔 are credited with the development. In 1967, James McQueen of UCLA developed and published the journal article, Some Methods for Classification and Analysis of Multivariate Observation. And the reason we point out this particular journal article is that this is actually the first publication to introduce the term k-means as a sequential clustering algorithm. Okay, so now that we understand a little bit about the history behind k-means, how does k-means clustering actually work? The main concept is pretty simple. What we can do is walk through an example of the k-means clustering algorithm on unlabeled data. So, what is k-means clustering actually trying to solve? At the end, we have to make sure that we satisfy a set of properties. So once we're done clustering, there's two sets of properties that we must satisfy. The first one being, each point must belong to a cluster. So k-means clustering doesn't allow for some points to just be unlabeled or kind of a question mark cluster because it didn't really fit well into any other cluster. Each point must belong to a cluster. And then the second condition it must satisfy is that each point can only belong to one cluster. That means no single point can belong to multiple clusters. So far, so good. So how does k-means clustering actually work? What we're going to do is, for visualization purposes, we're going to work with a simple data set with only two features, x1 and x2. It should be noted, though, that this general process is going to easily extend to n feature dimensions. I just can't visualize 8 dimensions on a slide. So, step 1, we're going to start with unlabeled data, which means we only have the features. So in this case, we would start with unlabeled data that has two columns, x1 and x2. And keep in mind, we're doing unsupervised learning. So we should note that if we had labeled data, so that would be 3 columns, x1, x2, and a y label column, then it wouldn't really make sense to cluster the points since you technically already have that y label. So this is why it's unsupervised learning. In theory, for whatever reason, this data set only comes with feature information. And we're trying to discover through k-means clustering the label. So we have this unlabeled data set consisting, in this particular case, of 2 features, but this extends to n features. Then in step 1, we're going to choose the number of clusters to create, and this is known as the k-value. And this is something you have to actually decide before you actually start running the k-means clustering algorithm. And later on, we'll talk about how to actually hone in and choose the k-value. So we're going to choose k is equal to 3. Note that in most situations, again, you're not going to actually be able to visualize the data in order to choose an appropriate k value. So right now, I can kind of tell visually that there could be maybe 2 clusters or 3 clusters, but there's probably not 8 clusters here. However, this is through a visual analysis. And if you're dealing with something like 8 features or more, you can't just plot it out and then visualize what a good number of clusters would be. So keep that in mind. We're going to have a deeper discussion on how to choose a reasonable value of k later on. For right now, let's just imagine that we're going to choose k is equal to 3. So step 2 is to randomly select k distinct data points. So I chose k is equal to 3, which means out of all these data points here, I'm going to randomly choose 3 of them. So we're going to say our k is equal to 3, and I've just happened to choose these 3 random distinct data points, and this is essentially my starting points for positioning clusters. So we're going to treat these new k points as kind of our cluster points, or the center of the starting point of the clusters. Then the next step is I have a bunch of remaining points that are not assigned to a cluster yet, beyond the 3 randomly chosen points. So all the remaining points, I'm going to assign them to the nearest cluster point. So that means, for instance, if a point is closest to the green point cluster, then it's going to get assigned to that green cluster. So eventually we get something that looks like this. I take a look and iterate through every single data point, and then based off the distance, so note here that distance metrics are going to be a really important part of k-means clustering, I'm measuring the distance to the nearest randomly chosen data cluster point. And now I've been able to assign everything. So again, we're just using a distance metric to judge the nearest points, and so far we've based this just off randomly chosen data points. So I said k is equal to 3, I chose 3 random points to start off the clustering algorithm, and then for all the other points that start off unlabeled, I went ahead and measured the distance between them and the remaining 3 random points that were already labeled, and then chose the nearest one. And now I have everything labeled. But obviously we want to iterate on this and improve on this. So what's the iteration process like for k-means clustering? Well, in step 4, we're going to calculate the center of the cluster points. Mathematically speaking, each point here is technically a vector of x1 in combination with x2. And this would expand to n features. You would have an n feature vector. So we know that we can take the average of vectors, essentially just the average of these points in this 2-dimensional space for x1 and x2. And then what I'm going to do is, based off the mean value of each point vector per cluster, I calculate the center of the cluster points. So I'm going to mark these as triangles. Keep in mind, these upside down triangles is not a new data point, and it technically doesn't really exist. It's just an actual center for the current existing clusters based off the mean value of the point vectors. So I calculated the mean value of the point vectors per cluster, and then wherever that mean vector cluster value was, I said, okay, this is the center of my cluster, and I'm going to mark it, just for kind of safekeeping, so to speak, with an upside down triangle. So then comes step 5, and here you can begin to see the iteration occur. I'm going to assign each point to the nearest cluster center. So now I'm going to iterate again through all the points and then check which cluster center is this particular point nearest to. And you can see here that on the top left I have that red triangle, and that blue dot right below it is actually closer now to that red triangle than it is to the blue triangle. So what's going to happen is, as I iterate through all these points, I may end up reassigning them to a different cluster center. And we're going to repeat steps 4 and 5 until there are no more cluster reassignments, which means for step 4b, and you can imagine we would say 4b, 5b, 4c, 5c, 4d, 5d, etc. And you keep repeating that. So now I need to recalculate the new cluster centers. Notice now what's going to happen is that red cluster center is probably going to move down. Maybe the blue one would also move a bit. Green wouldn't really move. And then after I recalculated the new cluster centers, what I'm going to do is assign points to the nearest cluster center. And in this case, all the points are currently assigned to their nearest cluster center. And this is just for visualization purposes. Obviously, I'm not being exact with my measurements here, but you get the idea. What I'm doing is I'm simply calculating that mean vector value for a particular cluster, assigning that as the center, And then I'm going to iterate through all the points and then see, hey, what cluster center is this point nearest to, and then reassign it. And I can continually do this until there are no more new reassignments, which means that cluster center is actually no longer being changed or moving around. So if there are no more reassignments, meaning the cluster centers are no longer moving, then we're done. All the clusters have been found or discovered. Now there are some upcoming considerations or questions we need to be thinking about. How do we actually choose a reasonable value for a k number of clusters? And the second question we should be thinking about, is there any way we can evaluate how good our current k value is at determining clusters? And that's kind of related to the first question. Basically, there's still a bit of mystery of how we decided at the very beginning that k is equal to 3, especially in real-world situations where we can't just visualize and plot out the data and choose a reasonable k value. So we're going to continue by actually coding out an example of k-means clustering, and then we're going to revisit those considerations of choosing the best k value when they naturally appear after we find the first set of clusters for a given k. So keep those questions in the back of your mind, and we're going to head over to actually coding out k-means clustering, and then once we get to the coding part where we actually have to decide whether or not we chose a good value of k, we'll come back to the theory behind a reasonable choice for k. Thanks, and I'll see you at the next lecture.